Thank you very much for the invitation for my late registration. I really appreciate being here back again. And I thank for the audience after such a tiring day to be still here and listening about this topic, the g-2 of the muon from lattice QCD and experiments, and if we have a 4.2 sigma. This is done in collaboration with the Budapest Marseille Wuppertal group. Some people call us BMW, and if you're interested in the details, you can find them in this reference. Unfortunately, I will be speaking about topology only one page, but I still think this is an interesting problem. And just to motivate that it is really interesting, it appeared in several newspapers when Fermilab published their new experimental result, and Nature published our lattice result exactly on the same day. It was not our wish, they did it on purpose. And actually it spent 2 weeks on the starting page of the New York Times, which is quite rare for lattice QCD. So it makes our community being visible to the larger communities. And it actually was chosen as one of the breakthroughs of the year 2021, both the experiments and the theory lattice QCD result. So what is it all about? And this is the picture which I want you to take home. So this is the g-2 of the muon, actually the half of it, that is called a mu, and only the 8th and the 9th digit of that. This is the Fermilab result of last April. This is the 20-year-old Brookhaven result, and that's the experimental average. And 134 physicists or so wrote a white paper and calculated the g-2 half, and that's what they obtained. And these two results are 4.2 sigma away from each other. And these are the publication details. And our result, the BMV lattice QCD result, is here. It is fully overlapping with the Fermilab result, and even with the average, there is only a 1.5 sigma tangent. And if you ask me what is the tangent between BMW and this white paper, it's about 2.1 sigma. So here is the outline of my talk. I'm finished with the motivation, and I will use this plot to show my outline. First, I will say very few words about the experiment, then about the white paper result. Then I will spend most of the time on the lattice QCD before I summarize. So let me start with the experimental result. I'm not an experimentalist, so my knowledge is very limited, but just to refresh our knowledge, what happened. So this is the a mu obtained by Fermilab, which has an error of 5.4 times 10 to the minus 10. It's an amazing accuracy. It is an accuracy that you're standing on your bathroom scale. The best equipment what the BMW group has, and you're losing one single eyelash. This fully agrees, as I said, with the Brookhaven result, though the Brookhaven result had a larger error. So instead of 5.4, 6.3. And if you combine, you will have 4.1. And the target for the Fermilab uncertainty in a few years will be 1.6. So if you want to improve on the accuracy, then it is necessary to have this 1.6 as a goal. Let me say a few words about the measurement. So since the muon is a charged particle, if you shoot it into a magnetic field, it will go around with a cyclotron frequency given here. Since it has a magnetic moment, it will precess with a slightly different frequency. And that's what you see here. So you shoot in the muon with the spin and the magnetic moment pointing to the direction of the momentum. And it will slightly go around faster than the particle itself. Actually, during each cycle, the spin axis changes 12 minutes. So how it is done? So proton on proton producing proton and neutron in pi plus. Then these pi plus are decaying to mu plus. And these muons are going around in this circle, and they are decaying to positrons. And there is a strong correlation between the spin of the particle and the E plus momentum. And since the spin is rotating a slightly bit larger frequency than the cyclotron frequency, you will see sometimes more, sometimes less positrons as a decay product. And then you detect these positrons and you see these curves, sometimes more, sometimes less. And since you have less and less muons in your storage ring, you have less and less decay product. And the frequency of these rotation gives you A. So that's actually what I wanted to say about the experiment to refresh how it is measured. So let me move on to the white paper. The white paper collects all the known physics contributions to the magnetic moment of the muon. The largest is coming from quantum electrodynamics, from photons and leptons. Then we have a smaller contribution from the electroweak physics, W, Z, X, whatever. And the most interesting contribution is a strong contribution, not because we are doing strong interaction physics, but I will tell you why. This white paper, which sometimes called the theory initiative, sometimes it is called the data-driven method, sometimes it is called the dispersion relation technique, sometimes it is called even the theory consensus value, because 134 people gave their name to that, has the following numbers. So the QED, as I said, far the largest, it has essentially zero error, at least on this level. Then the electroweak is much, much smaller. It is 15 times 10 to the minus 10. We should remember this 15. I ask you to remember to this number. It also has a very tiny error. And the strong contribution is 693. And essentially all the error is coming from this contribution. So I ask you to remember 15, 693, and these 4. So the strong contribution has several graphs which are contributing. This is the so-called leading order hadron vacuum polarization. And this has the dominant error. And I will determine this part in the following. Then we have next to leading hadron vacuum polarizations. These are much smaller. And the relative error is similar, but since the value is small, then the absolute value will be small too. And then for a long time, the so-called hadronic light by light was the difficult contribution. But in the meantime, both phenomenology and lattice reached a level where the error bars are subdominant compared to this one. And the reason for that, again, that the contribution is smaller. Although the relative error is large, the absolute value is small. So let me go to the vacuum polarization, hadronic vacuum polarization. And the traditional way, or these dispersion relation way, or the data-driven technique, or even the so-called theory consensus value is obtained by the optical theorem, which relates the forward scattering with the total cross-section. And people are using electron-positron to hadron data. So this is a gamma. It can be obtained by an electron-positron annihilation, and then it goes to all possible hadrons. And here are a lot of experiments which are working on this field, or which were working on this field, and it is systematics limited. So the number what you have seen is 693. The systematic error is 4 times larger than the statistical error. And the reason for that is that you have a lot of experiments, they have a lot of systematic uncertainties. And what you do using the optical theorem, you take these R ratio, the ratio between the hadronic cross-section and the muonic cross-section with some kernel function, integrate it, and then you have the hadronic contribution to the muon magnetic moment. And a whole bunch of people calculated that, and these are the 693 value. The next to leading order is a minus contribution with a small error. So that's what I said, we can forget it. And since it is around 10, and the light by light was also 10, they just numerically cancel each other. So there's no deep physics beyond this cancellation. This is just the fact that we are looking at the 693. And that brings me to the main part of my talk, to the BMW calculation. And please ask if you have any questions. It's late enough to do that. So what we are calculating is the electromagnetic current correlator, which is shown here. And it is also this integral with a kernel function. This KT describes the leptonic part of the diagram. And if I want to show you this integrand, KT times CT is shown here. And as you see, it is peaked around 1 Fermi. And I will say a few words what happened between 2017 and 2020. As you see, our data became far better. So the simulation setup has 6 lattice spacings in order to have a controlled continuum extrapolation from 0.064 Fermi to 0.13 Fermi. The box size is typically 6 Fermi, but in order to control finite volume corrections, we also have an 11 Fermi box. Then we have physical point in our simulations, or more precisely, we are all the time within 1 or 2% of the physical point. So here on this axis, I show you the proxy for the light quark mass. Here I show you the proxy for the strange quark mass. And as you see, it is really 1 or 2% within the physical value. So this is the ratio of the simulated value of the light quark mass and the physical quark mass. And here is the list of the simulations. Here are the beta values, A's, lattice sizes, and the number of configurations. And as you see, the more lattice points you have, the finer your lattice is, the more configurations you need. I said that I have one slide on topology. As you all know that depending on the action, the topology is frozen at 0.05 Fermi or smaller. And our smallest one was 0.064. So I will show you that it is not frozen. And to avoid these frozen situation, the CLS group is using open boundary condition. So let me look at these 0.064 Fermi and the topological charge at V zone flow time of 0.6 Fermi. And here it is changing very nicely. And if you measure the integrated autocorrelation time of the topological charge, it is 19 with an error of 2. So we save every 10th of the trajectories, and that means that every second of them is independent, meaning that blocking 50 or more of them is certainly not. There are a couple of new challenges in these calculation. Since we want to have a sub% error accuracy, obviously QED must be included. As I will show you, the lattice spacing, the absolute value of the lattice spacing is a crucial quantity. It is a challenge to have it at this accuracy. I showed you that the noise was reduced using these days, and I also mentioned the finite volume effect. So let me start with the scale determination. The lattice spacing A enters into the A mu determination at two places. First, at the physical value of the muon and the physical values of the pion and kaon. And if you do an analytic calculation, then you can convince yourself that if you have an error on the scale, the error on A mu will be 2 times as large. So this is the theoretical prediction. The numerical value is showing something like 1.87. So that's why you have to determine the scale very precisely. We have two methods. The one of them is the M omega scaling. That means the lattice spacing is the mass of the omega in lattice units divided by the experimental mass of the omega, which is very well known experimentally. And this quantity has a very light quark mass dependence and can be precisely determined on the lattice. And the other one is the so-called W0 scale setting, or Wuppertal scale setting, or Winter scale setting. It has a moderate MQ dependence, can be very precisely determined on the lattice. The only problem with it that no experimental value is given in the PDG as an experimental thing. So we determined it from M omega times W0, and here is the value what you received. And as you see, it is far better than 1%, far better, because it has to be far better. The other task was the noise reduction, and I showed you here the red points, which are the data at 2017. And 2020, we obtained a far better data, and that was reached by low mode averaging, all-to-all torque propagator in the infrared and stochastic in the UV, and another technique by replacing the correlation function by upper and lower bounds above a given T cut. And that meant that we reached a few per mil level accuracy on each ensemble what we had. Then the third one was the finite size effect. The typical latticetrons used 6 Fermi lattices, which gave a 2% finite volume effect. And as I said, we want to go below 1%, so you cannot accept anything which is a 2% accuracy if you want to reach a below 1% accuracy. So to reach a below 1% accuracy, far below 1%, we used not just a 6 Fermi box, this is our reference box, but the big one with 11 Fermi. So we calculated on the lattice the difference between the big and the reference. So A mu, the hadron vacuum polarization of this lattice minus this lattice. And we also determine this quantity analytically, and there are a whole bunch of analytic calculations in the literature, and we also did it, a few of them. So the lattice result was 18 between these two lattices with these errors. And this is next to leading order chiral perturbation theory, next to leading order chiral perturbation theory. Of course, you can forget it if you have the next to leading order. And these are other models, and you see that they all agree within the error bar with the non-perturbative result. But we don't need that because we have the non-perturbative lattice simulated result. But we wanted to see that we already reached the asymptotic behavior because these methods are better for larger and larger volumes. So that means that the difference between the big one and the infinitely big one can be calculated using these methods. Because already this difference was given fairly good by these methods. And the infinitely large minus the big one is calculated then by them, and it resulted in an error of 0.1%. Then I had the isospin breaking effects, and here is a summary of all those isospin breaking effects and all the isospin symmetric ones too. So this is about 1.5 dozens of contributions, and we presented it and hope that the community will check one or two of them or more than that. But it is published, everybody can check it. And the final result, instead of 693, is 707. So that's shifted up. And that's why our result is closer to the experimental one than the data-driven method. You remember it was 6.4, the error. This error is 5.5. And as you see, there is a factor of 2 difference between the statistical error and the systematic error. This result is also systematic dominant. The factor is only 2 and not 4, but nevertheless it is systematic. So what can I say about the systematics? There are a couple of results in the literature. Here are the results, and they are too uncertain to discriminate between these data-driven results and the result obtained by the experiment. So this is the hadron vacuum polarization on the horizontal axis. The blue band is the experimental result if we subtract all the known contributions. And these are the other lattice results. This is our lattice result, and these are the data-driven results. So this 5.5 is a 0.8 accuracy, and as I said, it is consistent with the new Fermi-Lab experiment. And it is 2 sigma larger than one of these results, which is very close to the white paper result, and 2.5 sigma larger than the so-called KNT result, which has the smallest error. Some people say that perhaps a little bit too aggressive. But anyhow, the discrepancies on this level, 2.1, at most 2.5. So before I finish, I show you something which gives us a tool to really go deep into the details of the lattice calculation and the systematics, and makes it easier for the other lattice groups to control our calculation. And this is a so-called window observable, which was suggested by the RBC UK QCD collaboration in 2018. And the idea is the following. So here you see the red curve, which is our 2017 data. And obviously, the large distance is noisy because large distance is usually noisy, infrared quantities. And the small distance has large cutoff effects because it is small. So what RBC UK QCD suggested to multiply the whole thing with a function which looks like that. So it cuts out the small distance physics and it cuts out completely the large distance physics. So just multiply it. And then you have a contribution to A mu. It is far less challenging than the full A mu. First of all, this is usually done only for the cheapest contribution or the easiest contribution to the isospin symmetric connected part. Then the signal over noise problem is essentially solved because you don't have these noisy part. The finite size effects are negligible because the finite size effects are appearing because you have large distance behavior. If you don't have large distance behavior, you don't feel the box. And the lattice artifacts here, the cutoff effects are also cut out. So according to our estimate, it is both computationally and manpower-wise 2 orders of magnitude easier than the full calculation. And here it is what we have. So this is these A mu light in the window, the isospin symmetric part. And this is the lattice spacing squared. Here you see the R ratio result, from which we subtracted some of the lattice contributions because they are not here. And this is the lattice results, the BMW lattice results. And we have used for the continuum extrapolation hundreds of thousands of extrapolating techniques. So using all the points, cutting down the courses, the 2 courses, 3 courses, using various functional forms, using improvement on the observable without improvement. So here you see with no improvement, here you see with improvement. And the central 68% is somehow the systematic error related to the continuum extrapolation. So that's what you have. And several groups have done it. And here I show you the continuum extrapolation of the other groups. So red is again our group. So this is the continuum extrapolation with no improvement. That's what you see here. And everybody is approaching 0 because I subtracted the final value just to see the cutoff effects. So the final value is subtracted, it gives a 0, but it shows the cutoff effect. So this is our result. The Oben et al. Result is very similar, small cutoff effects. Then the RBC has a somewhat larger cutoff effect. Then Mainz has an even larger, and ETMC has, according to this result, the largest cutoff effect. Let me emphasize again that this is the no improvement scenario. So with the improvement, it would be essentially 0. So, and here is the result, which I subtracted. So the final results of the various groups, many of them are preliminary. Red is the R ratio method. And these are the various lattice group results. And as you see, all of them are above. So they are scattered, but somehow all of them are above the data-driven result. And that's our result. And since this quantity can be measured very precisely. And you can calculate it using the R ratio method, dispersion relation. You can compare it, and you can reach higher discrepancies because the errors are smaller. Yeah? And indeed, here the tension is not this 2.1 sigma, but it goes up to over 8 sigma. And we are eagerly waiting for the other groups to publish their results on the window observable. Perhaps one more word on the window observable. The calculation was done using staggered fermions. And staggered fermions sometimes said to be good, sometimes bad, sometimes ugly. You all remember to be nice talk of Stephen Sharp many years ago. So we did the whole thing with overlap fermions for the window, because as I said, it's cheaper. And this is the staggered on staggered result, and this is the overlap on staggered result. And as you see, they fully agree. Actually, we use the local current instead of the conserved current, and this calculation is done on a 3 Fermi box, because that's even cheaper than a 6 Fermi box for overlap calculations. But the good news that it seems to be that they do agree. And finally, I show you just one slide about the continuum extrapolation. So we took the courses lattice, which was here. Yeah. These are various improvement procedures. But as you will see, all go to the same final value, and a finer lattice, which is here, an even finer lattice, which is here, an even finer lattice, which is here. Altogether 6 lattice spacings. I can show you here only 4. And then you extrapolate the continuum, and that's what you get. Again, 68% of the spread is interpreted as a systematic uncertainty. So that brings me to my summary. This is the published result for the various contributions, and this is the take-home message. Experimental result, white paper, 4.2 sigma, discrepancy. This is the calculation of the BMW. Essentially 0 tension here, very small tension there. And as I said, we are eagerly waiting for other groups to do the same calculation. Thank you very much for your attention.